Good. So we're moving and it's already recording. I'm going to start sharing my screen right in here. All the students coming. Here you go. Sorting a page break. Today is October the 2nd, 2023 is a Monday. Let's not forget exam 1, right? Exam 1 is Wednesday. The day after tomorrow. Tomorrow. And what did we, let's see, where did we stop last time, right? Okay, we're doing vectors. And we started with the components of the vectors, right? X and Y components of the vector. So let's take a look at the illustrations here. There you go, those are the vectors. We saw that. Remember that we have that if we do not know the components, right, we have to use that formula of the cosine law, so-called cosine law. But once you know the components, you don't have to worry about the cosine law, and all you gotta do is to use the Pythagorean theorem, right? And say here, oh, here you go. That's what we were covering last time, right? X and Y components of the vectors. But by the way, we also have the vectors cannot be just in two-dimensional space, but it can also be in the three-dimensional space. To visualize the three-dimensional space in a two-dimensional paper, right, is a little bit difficult unless you have a 3D computer program. By the way, Excel has this 3D capability, okay? It's it's not exactly easy to work with 3D with Excel, but yeah, it does have it. Ideally should be using, CAD, CAM programs. I have one that can help us plot things in the three-dimensional space. Okay, I used to use it a lot, and I like that program a lot. Let me give you an example of the three-dimensional. Oh, here you go. Here's a drawing, okay, of the three-dimensional of a vector, a three-dimensional vector plotted in the three-dimensional space. That's something that everybody can draw. Let's see. Program, okay, yeah, let's see. The one that I like the most, okay, so Ridwan is asking if I have a name for a program, such a program, right? The one that I like, but but unfortunately they stopped giving some support for that. It looks like they sold the program, but I like this program because it's pretty good. It can do algebraic manipulations as well. It's live math, but there are others, okay? Mathematica, for instance, right? And I believe, I'm not familiar with that. Mathematica I used to use as well. I was writing my PhD thesis in Mathematica, and then I discovered that Mathematica. Do you know Mathematica? Yeah, here you go. Mathematica plot in the three-dimensional space. Live math, I like live math because but let me show you live math, a sample of live math. Lately I haven't been using it because it has so many bugs in there, and they don't give you support anymore, unfortunately. Let's see, live math. And there is also Google, right, has a free software. I'm trying to remember. I believe it's Sketch. The name of it is Sketch, right? Yeah, live math. That's right. Let me. I can't. Oh, it looks like. Oh, I uninstalled my live mass here, unfortunately. I had to, oh gosh, I cannot show you that, but we can go into their website. I had to reformat my disk, and in the process, right, I uninstalled my live mass, and I did not reinstall it. Let's take a look here. Live mass maker. Here you go. Live mass maker. Live mass maker. Here you go. That's the one. See, they have simple graphs, right? But they also have 3D graphs as well. They also have 3D. It's not just a plotting. So, oh, here you go. Some samples, some 3D samples that they have. Here's the z-axis. This one must be the x-axis, and this one is the y-axis, right? X, Y, and Z. Okay. And yeah, I don't. Yeah, unfortunately, I cannot show you that here in my computer because I uninstalled my live math and didn't reinstall it back when I have formatted my hard drive. That's livemass, livemass.com. Live Math Maker, right? Live Math Maker is the name of the product. And download. Let's see, there's a free trial, right? And we also have Mathematica. I have Mathematica installed in my computer, not this computer, in my other laptop, in my laptop. And I need to transfer the Mathematica programming, Mathematica Online. Here you go. Mathematica, wolfram.com. This guy, they came up with this Mathematica program back in the late 80s. Okay, I was using it a lot for my PhD thesis, and then I discovered that there was a bug in the computer at that time, right? They fixed the bug later on. They had a bug in one of the functions, and I just stopped working altogether, and I just went to Fortran programming to Fortran. Let's see, Wolfram Mathematical 13 version 13 is here. See that? You can do 3D plotting, and you can do other things as well. You can do other things as well. Algebraic manipulations, you know. You can do Mathematica, but the live math has a better user interface. Here. Of course, the graph of Mathematica is nicer, but not the display of formulas. The display of formulas is better in live math. And there might be others too that I'm not familiar with. Okay, anybody has any experience with that? Anybody has any experiences? CAD, for instance. I never use CAD. I know it exists. I know it does 3D. And there is, I'm trying to remember another one. Well, if I remember, I'll let you know. Okay. But yeah, that's live mass maker. Let's see, purchase, right? Let's see how much they're charging for that. I think it's around $100. Purchase a feature, get upgrades, live math maker, price for students. See that? $29, 3 months, 6 months, 1 year. I think that the lifetime of the software, something around $100 or $200. Oh yeah, here you go. Student, individual, academic, institution, commercial. Okay. Wow, they increased time unlimited to $400. Huh. Interesting. Academic institution. Okay, I qualify as an academic institution, hopefully. Individual. See that? $200 for individual. Yeah, 200. Academic institution is more expensive. Yeah, that one looks like that was the one I bought, right? For individuals. Now for students, you have those three: unlimited time. And I visited those guys several years ago. They're in Boston. They received me very well at the time. Okay, but if you don't have a software, you have to imagine, right, the X, Y, and Z axis in the three-dimensional space. You start practicing that, okay? So you can have an illusion that the vector is deployed in the three-dimensional space. Doing a two-dimensional vector is no big deal, right? The thing here is to visualize the vector in the three-dimensional space, and that's the little trick that we do. Here's the XY plane. This line here is along the XY plane. This line here is parallel to the Z axis, right? This line, this vector is parallel to the Y axis, and this vector here is parallel to the X axis. That's why I put AX, AY, AZ. And then I call this one the AXY because it is in the XY plane. When you sum AX plus AY plus AZ, you get this red vector. Nope. Better use cat for some vector stuff. Okay, good. Solid. Okay. So we can adapt our notation. It's not difficult. Our mathematical notation for the three-dimensional space. Okay, vectors in the three-dimensional space. Vectors in the 3D space, right? I'm going to copy. It's not much different. Okay, so here you go. I'm gonna copy this one here. No, I'm gonna do like that. Let's see here. Oh, here you go. Example. All I have to do is to add, right? Let's see. I'm going. Yeah, here you go. I'm gonna copy the whole example here, the whole two-dimensional example, and then all I have to do is add a component, a Z component to our example. Okay, A is x 5x hat plus 7y hat. So here you go, plus, let's say, 8z hat, right? Like that. So I'm adding a Z component to my two-dimensional vector. And I can do the same here for this other, for the B vector. I'm gonna put Z hat. Oh, didn't do it. Let's see now. Yeah, work it. Right? Find the A plus B vector. And now we have to add this component here. Just repeat what we did before. Just adding this other component. It's very similar to the problem that we did for two-dimensional, right? See, that there is no secret, right? It's just a little bit more complicated mathematically. And, 5x sum up with 1x. 7y hat sums up with 10y hat. And now we have to sum the x hat. Now we have to sum the 8z hat with the z hat, which ends up being 9z hat, right? And let's see if, and then, okay, the other example, right? The other example is to find the magnitude of this vector. Okay, and we should apply the Pythagorean theorem, right? We should apply the Pythagorean theorem. Here we go, we gotta add my 9, plus some plus 9z hat, right? All those three vectors, x hat, y hat, z hat, they are perpendicular to each other. They're all perpendicular to each other, right? And consequently, their magnitude is going to have another term here, 9 2 square. We can visualize that very easily in the three-dimensional space, right? So here you go. See, that's the AXY components, right? The AXY component is the vector in the XY plane. This vector here in the XY plane, the magnitude of this vector in the XY plane is going to be AX squared plus AY squared, right? And now, because this vector is perpendicular to this vector, the vector in the xy plane is perpendicular to the vector along the z-axis, we just add, that square that you saw to the square of this one, right? In general, right? In general, vectors in the 3D space. Vector in the 3D space has a z component, right? And I'm going to write like that. In the most generic way, I'm going to write like that. Let's say, in the most generic way, the A, here's the notation, the generic notation. AY, AZ, right? That's what we're doing with numbers. These numbers here, AX, AY, AZ, those scalars, AX, AY, AZ, can be either positive or negative, depending which direction those components are pointing, right? If the components are pointing in the negative X direction, negative Y direction, and so on, they would be negative. Go, right? So if I want to, to find the magnitude of A vector, right? What that would be? The should be AX squared, right? AY is square and AZ is square. I gotta remove that. But let's not forget, this is the square of the magnitude, not the magnitude itself, right? The magnitude will be the square root of that. And then we put the square root right in here, like that. That's the genetic formula. If we want to find out the angle that the vector A makes with the z-axis, now you need to visualize. Now you will need to visualize the disposition, right? The disposition of the vector in the 3D space. Now I have to visualize. So here you go. You want to know this angle here, right? I even already put the angle. This angle here, let's see. The tangent of this angle here is going to be what? The magnitude of the vector in the xy plane divided by the magnitude of the z component of the vector. Make sense? Right? Similarly, if you want to know the angle that this projection makes with the x-axis, right? All you need is gonna be the tangent of this angle is gonna be AY divided by AX, right? But let's just put this one here first. If you want to find out the angle, I'm gonna put angle theta that the vector A makes with the z-axis, you will need to visualize, right? You will need to visualize the disposition of the vector in the 3D space. And I will call this angle the angle theta, just like I mentioned, right? Tangent of theta. Yep. Going back. AXY, right? The length of this side. AXY divided by a sub z. Yeah, divided by a sub z. A sub xy. And going back there, we can replace my axy with this value here, right? If the other one, if you want to find out the angle, let's say phi, right? That the vector along the xy plane, axy, makes with the x-axis, this one's gonna be easier, right? This one's gonna be easier because you do not need to visualize the disposition of the vector in the 3D space. You know, it will be easier, right? Comma, it will be easier because you do not need to visualize the disposition of the vector in the 3D space, but only its axy component. Axy component. Okay, so here we go. And I'm going to, now I'm just going to, oh, what did I do here? Let's go back, Oh, this one. Okay, this one here. Now all I need, let's see. Suppose I'm looking from the top now, right? Suppose I'm looking from the top. Suppose I'm looking into the z-axis, right? You're going to see the x and y axis like that. X and y axis like that. Now, I might need that, so let's move this one, right? Okay, so what am I doing? My eye is pointing from the top of the z-axis, right? And I'm going to see the x going down, the y going to the right. That's why I drew the x, y like that. All right. And then we are going to have a x component of the vector that's going to be somewhat like that. We want to see the z component, right? Because we're looking into it. And the y component of the vector is going to be this one here. And we got axy subscript. And we want like that. I am going to document it. Okay, we do not have the z-axis anymore. The z-axis right in here, pointing toward your face. Okay. And I will label this. You know what? I'm gonna put alpha. That's easier to write alpha. Right? A symbol alpha. Let me change the notation there. It will, if you want to alpha. this angle here, we have a right angle triangle here. It's going to be a sub y divided by a sub x. Oops. Oh, whoa. This one here. Good. A sub y by a sub x. Okay. Have anything else? Let's see. Yeah, that's what we have. That's all you have about vectors, mathematical vectors. Now all we have to do is to start working on the vectors on physics, the physical vectors. Illustration. Give a little bit of a break so you can get your thoughts together. See where you are. We are writing here. Okay, and we are going to start 2D motion. Now that we finished the vector, we are going to start 2D motion. And hopefully we have enough time to start the laws of motion most like we want. Huh? Let's see. Don't forget Wednesday is the exam, right? Material up to September 27, excluding vectors. Vector is going to show up in exam 2. Let's take a look at the SketchUp. You know, regarding the 3D program, I think that Google has a computer program that I started using some time ago called SketchUp. Okay, and it was free of charge. Okay, so, oh no, they're charging. Oh gosh. There must be another program. I don't see SketchUp. Google's, 3D software, 3D software. Yeah, here goes, free 3D software. 3D CAD design, those are sponsored one. SketchUp 3D modeling software. SketchUp, okay, they have a free version of SketchUp. Okay. Yeah, you can draw a 3D object. You can also draw. Oh, you can also do that with PowerPoint, okay? But it's not as powerful as other software. So we have this, if they have this, you know, gotta look if they have the axis, right? X, Y, Z axis. And SketchUp and Google SketchUp to this software, free download. Yeah, it's a Google software. Download free, SketchUp free. It's the simplest free 3D modeling software on the web. No strings attached, right? I also started looking into that too. But then I gave up because it's just difficult for me to learn. But let's go to Wiley Plus. Go to Wiley Plus. And here's the Wiley course resources. Come on. Here. I need to post this guy here. I will do that. Publish, right? Let's wait. Okay. Launch. I want to locate you where we are in the book. Okay, chapter 1, right? Trigonometry. Well, I don't cover trigonometry because it's already, a requirement for this course, but we're doing this one here. We just finished this one. Scalar and vectors, vector addition and subtraction, components of a vector, addition of vectors by means of components, right? That's what I did. So let's document that in the notes. So far, for exam 2, right? Now I'm talking about exam 2, not exam 1. And, I guess I mentioned that to you before, right? All those special effects in movies like Avengers, right? Just like he said, relies on computer and mathematical concepts. And even the Interstellar movie also, if you watch it as Interstellar movie, that's pretty good. It's very impressive, not just the story, but also how realistic they did. They rely on very powerful computers to do those movies, and you need to know mathematical concepts to do all those special effects. Okay, when I used to work a lot with my live math, I understood what math is involved in plotting 3D objects. Okay, and believe me, those guys in Disney, those guys that make movies and special effects that are using those power, and by the way, they use very powerful computers to do that. Okay, they do have to know their math to come up with those special effects. In the Interstellar movie, for instance, and their math, it's all related to vectors. It's all related to X, Y, and Z components. Okay, in the movie Interstellar, for instance, they hired a scientist to visualize the black hole in the movie. They did, and the guy and the scientist that went join the production, he was impressed with the computer that those guys had available. Very powerful computers. And he was able even to write papers, okay, out of that simulation that he did. Okay, I was reading an interview of that guy, and he was telling me, look, I came up with simulations of different black holes under different conditions, no, and even came up with the drawings how the black hole would look like. The scientist would not make a decision on which simulation is going to end up in the movie, okay? But the scientist would brought all different options, right, to the producer, to the director of the movie, and the director, of course, would have the final say which one they were going to use. Okay, the scientist didn't have the final say, but the scientist was powerful enough to show, look, you can use this one, you can use this one, you can use this one. Which one do you like? Would you like to use for the movie, right? And then the director would pick up, oh, I want to use this one here. And it was a scientist who did all those mathematical calculations that result in a very realistic depiction of the black hole in the movie Interstellar. And it's no different in those Avengers movies. Iron Man, Avenger movies and so on. Black Widow, right? They have to use those powerful computers that they have at their disposal. Imagine doing that, producing those things in an IMAX screen, right? Even more powerful computers, not just the flat screen, but is a far more is a movie that has far more resolution than the regular movies that we have out there. But those are the sections of chapter 1 that we just finished covering. 1.5, 1.6, 1.7, and 1.8. I'm going to write that down here for you. So far, for exam 1, sections 1.5, right? 1.6, 1.7, and 1.8. Yeah, 1.5 is scalars and vectors. Scalars, vectors. 1.6. Vector addition, subtraction. Subtraction. 1.7. Components of a vector. Vector. Oh, not this one here. And 1.8. There are more, for example, 2, of course, right? 1.8 addition of vectors by components, right? Addition of vectors using their components. If I'm going to solve a problem and I can do that using addition of vectors by their components, I prefer this technique here instead of messing up with the cosine law. Okay, this one is very straightforward from the mathematical viewpoint. And I didn't finish those examples, right? Those numerical examples. Go, and then you finish. Okay, can you please finish, right? It's going to be that value that you saw plus 81, right? Plus 81. Oh, when I start doing that, I went to doing the more genetic one, right? And I'm not going to put the final result in this way. Okay, with the z-axis, right? With the z-axis. And that's going to be what, a should be 17, right? So, no, 17 plus 36, 17 square plus 36 plus 36, right? And then we have a square root here. And we have, is that, let's see. Yeah, the AXY, and then we have the Z component here. This one, let's not forget, 9Z. I'm gonna put 9Z here. Divide by 9. I'm not gonna finish it. Is that right? Yeah, that's right. 17 square plus 36 is square root of that divided by 9. 932. Let me save that, and I will take attendance now. Attendance, your roster. Roster, let's do this one here. That's the lab, that's the lecture. 9:33. Today is the 2nd of October. Yeah. 2nd of October. We have very few students today. Huh? Everybody's getting ready for the exam, I presume. Sky, are you there? Sky Carvajal. I don't see Sky. Tessa, are you there, Tessa?
I'm here.
Okay, thank you. Destiny. I don't see Destiny. Gael Garcia. I don't see him there. Ridwan, definitely he's here, right? Let's say you're there. We don't. Thank you. Ashley. I don't see Ashley. No. Yeah. Norberto. Okay, thank you, Norberto. Annabelle.
I'm here.
Thank you. And Eric Martinez. Let's see, Eric. Doesn't look like Eric's here, right? Nope. Vanessa. Vanessa Menon.
Here.
Thank you, Vanessa. Nazmoon. I don't see Nazmoon is here. Right. Catherine Pacheco. Thank you, Catherine. Camden.
I'm here.
Thank you. Victoria Preciado.
I'm here.
Thank you, Victoria. Alexis Richardson. I don't see Alexis here. Okay, Robinson is not here. Marco Sanchez. Marco Sanchez is here. Okay, let's see if you have, what, must have 9 students, right? Yeah, 9. Okay, everybody answered to that. 9:35, we still have some time ahead of us. And what we're going to do now is the next chapter. That's going to be kinematics in 2 dimensions. We did kinematics in 1 dimension. Now we're going to do kinematics in 2 dimensions, okay? This section right here. It's a little bit more difficult because we're doing kinematics in 2 dimensions. Is a little bit more difficult because we're dealing with a second dimension. Mathematically speaking, it's more complicated. Physically speaking, is almost the same. Almost the same. It's a from the physical point of view, it's a combination of 2 motions, one along the x-axis, the other along the y-axis. Okay. And let's not forget, when we do those, when we teach this type of course, we don't go, it's a lower level physics, this one, okay? Because we're teaching lower level physics, we do not go into the 3-dimensional space because it becomes too heavy in mathematical terms. But in real life, yeah, people treat the motion of objects in the 3-dimensional space. That's real life, right? If you're going to work for the military, you want to find out, just like I said, it's just like your Patriot anti-missile system. The Patriot anti-missile system is working in the 3-dimensional space. And the problems that we have to solve with the Patriot missile system, it's far more complicated than what we do here. But before you start to understand the motion of those anti-missiles in the theater, in the battlefield, in the battle theater, right? You have first to understand what's, how those problems are solved in 1 dimension and then in 2 dimensions. Okay. So, and what do we do? Okay, we started with the displacement, velocity, and acceleration vectors. And then, remember, right? Not everything in physics is a scalar. Some things in physics are scalars. Some other things in physics are vectors, right? I believe I came up, okay, let's see. It's scalar quantities. That you have to memorize, okay? Length is not the same as position. Not the same as position, right? Position is one thing, length is something else. Time, right? Mass, those are 3 scalars. And then we have the other scalars, which is what? Distance traveled and speed. Right? Primary, right? Basic quantities, those are the basic quantities. And those basic quantities can be used to find the other definitions that we have here. And then we have the vectorial quantities, vectorial quantities. Okay, vectorial position, right? Position is a vectorial quantity. Force is a vectorial quantity. And now we have others, other vector quantities. Displacement is one of them. Velocity is another one. And acceleration is another one. Right? Scalar and vector quantities. Okay. I'm going to put a little bit here. I'm going to justify a little bit here. Like that. Right? So we have it nicely organized. Right? You know, the vector position, we usually denote it by the notation R. R with a vector symbol there at the top. Yeah, lowercase r. The force vector, we usually denote it. We didn't come up with the force yet, right? We didn't start talking at depths with force yet, right? But we denote it by the vector F. The displacement vector, we denote it by the symbol delta R. Delta R. The velocity vector, we denote by the symbol V. And let's not forget, there is average velocity and instantaneous velocity, right? I'm just simplifying that. And right now, I'm just simplifying that. But when we get into that, I will tell you. I will go through that, okay? One, two, three. Can you remember that? No, actually, we already have 5 different vectorial quantities, right? Here we have the average velocity plus instantaneous velocity. Here you're going to have the average acceleration plus the instantaneous acceleration. So if we count, it's going to be 1, 2, 3, 4, 5, 6, 7 vectorial quantities. And let's start treating that in more detail. Okay. And remember, first we're going to look into that into more detail further down the line. Okay. Not yet. I'm not going to talk about force yet. Okay. So let's take a look here at here you go. Suppose, remember we were talking about the motion in the two-dimensional space. Here I am illustrating a genetic path along the XY space, the XY plane, not space, but the XY plane, right? So I've given the instant of time, the particle is here, then it's here, and then it's here, and so on, as time goes by. We're going to illustrate something far simpler than that, by the way. Okay? So here you go. Initially, let's say this particle is at this initial position. See that? The initial position vector. And I'm denoting it as being x naught, comma, y naught. Okay? X and y. Here's the x component of the position, right? Here's the x component of the position, and here's the y component of the initial position, right? As time goes by, try to visualize in a movie, right? How does this vector change as time goes by, right? It starts here, and then a little bit later on, it starts to go elsewhere until it reaches this point, right? And here I'm denoting final position, initial position, right? So in this specific case, the vector position is a function of time. I'm going to put like that. Here you go. Vector position is a function of time, right? As time goes by, the vector position changes, right? And then once we have defined this vector position, once you have a picture, right? A specific picture of this vector position, we can start talking about the other definition. The other definition, which is the vector displacement, right? So here you go. I'm going to write that down in my notes. Vector displacement is defined exactly in the same way as the scalar displacement. Is going to be the final position. Let's see, that final vector, final position minus initial position, right? And it's very easy to picture that in terms of a vector summation if I move the R naught to the other side, right? Here you go. The final vector position is delta R plus the initial vector position. Let's look at that. Final vector position is the R naught plus delta R, right? Here we are doing the head to tail method. Head to tail method illustrates perfectly how delta R relates to R naught and RF. Two different ways of writing that equation. Either delta R is RF minus R naught, or you can write it down. R naught plus delta R is equal to the resulting vector. Okay. Here you go. Here's another way of illustrating that. Right? Here you go. RF plus minus R naught, right, is equal to our delta R. This vector here is equal to this vector. That's another way of visualizing it in the XY space. Okay? Those illustrations are very useful, okay? Those illustrations are very useful because the average velocity vector is related to the displacement vector. You know, remember? Average velocity, right? Gotta put here you go. Is related to the displacement. Yeah. The average velocity vector will be parallel to the displacement vector. Make sense? This thing here is a scalar. It's not a vector. Those are two different quantities. Okay. So here you go. That's what I drew right in here. The average velocity vector is going to be parallel to the delta R vector. Okay. Here you go. And what I want to do right now, let's take a little break, right? And then it's almost 9:50. Any questions before we move forward here with our break? So, okay, break from 9:50 a.m. to 10:05 a.m. Okay. And what we are going to do, what we are going to do, we're going to do exactly what we did for scalar quantities. That's exactly what we're going to do. It's going to be a little bit more complicated because it's a vectorial. So those are vectorial quantities, so we have to look at other types of concepts that are going to show up in this case, okay? So any questions? Okay, so let's take a break, and I see you in 15 minutes. I am back here, and here you go. We start this topic right through the motion, the topic of 2D motion, and we have here a genetic path of a given object in the x and y plane. In order to study 2D motion, we have to have this path, okay? And then we have this initial position, right? Notice that I put here x naught, y naught, right? And I'm going to continue using x naught, y naught here, right? And we have this final vector position that, by the way, is also going to have coordinates. Let me get that T2 here. It's very useful to have the coordinates here, xf, yf. Recall that in general, we drop this lowercase f, right? I put T2. There's a reason why I put T2, okay? There's a reason. So once we have that, there we go. That's a more simplified version of the same slide, right? I can put it right here before that. Yeah. And now we have this vector displacement delta r, right? And then I'm going to do more about that. Displacement vector delta r. Recall that rf can be denoted as being x sub f in the x hat direction plus y sub f in the y hat direction, right? And r naught is the same thing. It's exactly the same thing. The only thing that changes for r naught is the subscript x naught x hat yf x hat. Okay, so when we take this rf minus r naught, right, we can expand it to become something slightly different. Like that. Like that. And then we can further, right, can write in a better format. That's going to be xf minus x naught yf minus y naught. Which, by the way, becomes delta x plus delta y. like that. Okay. And this one, I want to move it upstairs, right? Which is just another way of showing to you how delta R related to R naught and RF. And then we have the average vector velocity. Average velocity vector. Average velocity vector. Here we go. Is going to be something like that. Right? And look, there is a nice relation here that you're going to see. Let me get this one. Oops, this one here. Right? And I'm going to do even better. I'm going to put this x hat outside this ratio so you can appreciate how this relation is also broken down in terms of components of the velocity, of the average velocity. What you have here is the x component of the velocity of the average velocity vector. And what you have here is the y component of the average velocity vector. Delta x over delta t, delta I over delta t, right? So I can here write that as a scalar, right? Average, AVG. And this one here, y average. X component, y component. Okay. And I'm going to remember every vector, every two-dimensional vector has an x component and a y component, right? Make sense? So I'm going to, here go, average velocity, right? And I'm going to here write that as being AVG. Nope. Okay, now I can do it. AVG. Next in line is going to be my instantaneous velocity vector. Instantaneous velocity vector. And I denote it just by the V with a arrow without the AVG, right? Okay. See here. Okay, right in there. And I'm going to do something else. I'm going to do something else. Let's see if I can get, yeah, here you go. I'm gonna get that and I'm going to show to you the components of this displacement vector, right? The displacement vector has two components. One like that. Grid lines. And I'm gonna put a dashed. Okay. Gonna be a little bit, yeah, better. Yeah, this one goes here. That's going to be the component of the x component delta R. And this one here is going to be the y component of delta R. Y component of delta R. Oh, like that. Likewise, the average velocity vector is going to have x and y components as well. Let me take this one out. So, oh, I'm going to need the grid lines for now, right? And by the way, I'm going to emphasize that the average velocity, not good. Nope, doesn't like it. Yeah. Oh well. Yeah, okay. Now we have it, right? I'm emphasizing that the average velocity vector is parallel to the delta r vector. Okay. And what I'm going to do here, I'm going to illustrate that the average velocity vector has an x component and a y component. This is going to be just like my delta r has. How did I denote that there? Let's see. First the x, right? And then the average, yeah. I'm going to copy that and paste in there. Yep. Move a little bit here. Becoming busy, right? Okay. T2 is going to go here. So far, there is nothing new what we're doing here, right? What we have been doing here is very similar to what we did in the one-dimensional space. Well, things start changing whenever we introduce the instantaneous velocity. Then we start to get some other types of concepts here that are not obvious. Okay, the instantaneous velocity vector is defined as the, let's go back to our one-dimensional definition that we saw before, right? So I'm just going to copy and paste what I have here. Average, where the instantaneous are right in here. Paste. What we're going to have here for the instantaneous velocity vector definition is going to be something like that. And instead of delta x going to 0, it's going to be my delta r that's going to go to 0. Okay. Put the limit in here. Right? And now it becomes delta x goes to 0 and delta y goes to 0 because delta r is no longer there in the definition. Delta r vector is no longer there in the definition. Okay. And then we break down. We should put a parenthesis here. Make sure we put a parenthesis here. And now we do not need the delta y anymore. We do not need for the first term, right? Yeah. Okay. Like that. Sometimes can get a little bit tricky to handle this software. It's not ideal, but it's better than keep on writing under other conditions, right? Yow. Okay, I gotta do something else. Okay, now we got it. And then I'm going to do the same for the next term, but instead of delta x going to 0, it's going to be delta y going to 0. Right? There is one more step that we can take here. What's going to 0 is delta x and delta t is not x hat, right? So I can take x hat out of this limit. And I also can take y hat out of this limit. Okay? And we end up getting something like that. Right? Something like that. So how do we illustrate that in this graph, right? Let's see. Okay. Illustrate it in the following way. As delta t goes to 0 simultaneously with delta r, right? Delta t goes to 0 simultaneously with delta r should be something like that, right? Delta r is going to 0. Delta t is also going to 0, right? So here you go. Let's do it this way. I'm gonna take this one out of here. And I'm gonna state that's gonna be my T1 now. That's why I put T2 initially. As delta T and delta R goes to 0, something interesting happens. The resulting velocity vector, ends up tangent to the path. Okay, in the limit where delta r goes to 0, r naught coincides with rf, right? And my delta r is going to be tangent to the path. Consequently, my velocity vector is also going to be tangent to the path. Okay? Remember, there is even a that's the graphical way of visualizing that, right? That's a graphical way of visualizing that, right? But the mathematical way of visualizing that would be to look at the tangent of the angle that the velocity vector makes, instantaneous velocity vector makes with this path, right? Note that the tangent that the velocity vector makes with the path is given by tangent theta dy over vx. Right? And Vy over Vx, right? What's Vy over Vx? Is this limit here? This limit of one over the other, right? And look what happens to this limit. This limit can be rewritten in a different way. This limit can be rewritten as though as, see, okay, can be rewritten as though as we have, oops, I forgot the equal here, delta y over delta x, which, by the way, we do not need the delta t anymore, because we cancel out the delta y, the delta t. I'm gonna use this one here, delta x, okay, which is nothing but the tangent, right? What you see here is the tangent to that curve. So I prove to you, that the velocity vector is tangent to the path of the particle in both ways, both graphically and mathematically. The above means, the above means that the velocity vector is tangent to the path of the particle. So what does it mean? At each point in the path, you're going to have a velocity vector that's going to be tangent to the path. Let's not worry about the acceleration yet, right? Let's not worry about the acceleration yet. Let's worry just about the velocity vector. Here you go. At this point, we have one velocity vector. At this point, we have another velocity vector. At this point, we have another velocity vector. At this point, we have another velocity vector. Different, oh, we don't need that equation either, because we didn't get there yet. Different velocity vectors have different directions along the path of the particle. So that's the interpretation for the velocity vector. Okay, is always always tangent to the path of the particle. Don't need that. Always. The instantaneous, right? That the instantaneous is always tangent to the path of the particle. And that's where we come to the point that we can define, right? We can define the average acceleration vector. Find the average acceleration vector. Okay. The average acceleration vector has a definition similar to that of the average velocity vector. So, but instead of delta r, we are going to have delta v here, right? Instead of delta x, we are going to have delta vx, right? Instead of delta y, we are going to have delta vy in the y direction, right? So here we go. And then we are going to have a x component of the average acceleration vector, the y component of the average acceleration vector. And by the way, let's not forget, right, that what we have here is final velocity minus initial velocity. Oh, that's what we have here. If you want to spell out here too, final velocity in the x direction minus initial velocity in the x direction, right? Final velocity in the y direction, you can. So let's keep the notation short. Let's see how it is illustrated in the graph, right? So suppose I want to know the average acceleration between those two instances of time, v1 and v2, right? Right? Instead of 2 minus 1, I'm going to put final, initial. So how do we illustrate that? Okay, so let's see if I have a, oh yeah, I have it here. That's v1. That's v1, right? And that's v2. If I do v2 minus v1, I preserve the direction of v2. This guy is exactly the same as this one. Same direction. And then we gotta get the minus v1 vector because that's what it's spelling out here, right? In sum the v2 with the minus v1. v1 is to the right, minus v1 is going to be to the left. When we sum them up, we end up getting an average velocity vector that is in this generic direction. So all I did here was transplanting this velocity vector to this point here. It's parallel. That's how we find the direction of the average acceleration vector. Whoa. Barulheira é essa? Okay. We have some construction going on here. Okay, so let's write it down here. Looking at the illustration, right? The PowerPoint illustration. And before we go to that, let's do the second one here. If we repeat that for, let's say, this two pair, those let's say, if we repeat that for those two pairs, V2 and this other one, we get something similar. Well, okay, and what else do you have to know? You have to know that the average acceleration is in general, it points towards the concavity of the pass. Do you see that? This is not a coincidence, okay? If you have a concavity here, the average acceleration is going to point towards the concavity, not away from the concavity. So what you see here is an acceleration vector. Here's another acceleration vector. Here's our first acceleration vector. And that's what I want to write next. With the PowerPoint illustration, we know, see, that the average acceleration vector points towards the center of the concavity of the pass. And again, the thing is another piece of information that we do not have for the one-dimensional kinematics. This is no coincidence. This is no coincidence. Okay. So what we have next, let's see here. Here you go. Here's the average acceleration. That's not the average acceleration. Those are now the instantaneous acceleration vector. Okay. When we take the limiting condition out, we have this type of acceleration vector. It's always pointing towards the concavity. Okay, you may have something like that. You may have something like that. You may have something like that. But we will never have an acceleration that's away from the concavity, right? Okay, whether it's for the average acceleration or the instantaneous acceleration. More precisely, the instantaneous acceleration is like that. Okay. So let's the instantaneous acceleration vector follows from the limiting condition or okay, limiting condition. Yeah, I'm gonna do like that. A limiting of delta V over delta T. Okay. Its resulting vector is always pointing towards the concavity of the path. Okay, so here you go. And we have, by the same token that we have x, by the same token that we have the x component of the acceleration plus the y component of of the acceleration, can also find different set of components. Sometimes it's more convenient. Sometimes, we can also define a different set of components that is more convenient. Tangential component and the radial component. Tangential and radial components. The tangential and radial components. Tangential to the path, that will be, i.e., the components that are tangential and radial to the path. Okay, and that what we have right here. Here you go. So if you have an acceleration vector that points in this direction, it's still towards the center of the concavity, right? This acceleration vector is going to have a tangential component and it's going to have a radial component. Now, this other acceleration vector barely has a tangential component, right? You can see it. The tangential component is going to be always in the direction of the velocity vector. But the way I illustrated this the acceleration vector component, this one has a tangential component almost zero, right? Has a very small tangential component. Most of it is radial. It's not exactly radial because it's pointing towards the center, right? It's minus the radial direction. And here too. Okay, so here we go. Just it looks like we have a revision here. Yeah, okay, that's what you have. Yeah, we can. Those are the things you have to know. That's a very generic treatment. We are going to start looking at more. Okay, this is a very generic treatment of these vectorial quantities. What we're going to do next is to come up with a specific examples. Okay. And I want to take this chance to have a break right now. And do you have any questions?
I have a question.
Someone has a question there?
Yeah.
Can you speak
What
up?
is token?
Yeah.
Hello?
Yeah, 1 minute. There's too much noise here. Can you type there in the chat window?
Yeah.
Okay. You didn't say anything about token. I don't remember saying anything about token. How to determine the concavity of the path. Okay. Okay. Yeah, same as token. I don't. Well, how to determine concavity of the path is going to depend on the path, on the particular path. Okay. We are going to look at examples that that is going to have a specific concavities. I'll try to talk to the people there upstairs to, you know, stop doing this work. Okay, so we can have a better class. Okay, so let's go have our break. Break from 10:47 a.m. Right to 11:02 a.m. Okay. So I see you 11:02, right? 02. I see you soon. Okay, I'm back here. 11:03, right? So let's look at the examples. At 2D motion examples, right? What we did so far is just a genetic treatment. Okay? With actual examples, you will have a better idea of these concepts, right? That I spelled out. So let's look at some 2D examples, 2D motion examples. And okay, one of them is that of the projectile motion. That's one of them. That's the one that it's a must to treat. Okay, we always treat that projectile motion. And what's projectile motion? What is projectile motion? Right, it's just like free fall. It's projectile motion. It's free fall in 2 dimensions. Or in 2 dimensions. Right? And free fall, how is that defined too, right? Free fall in 2 dimensions and projectile motion in 2 dimensions is motion under the is motion, whereas an object is subjected only to the acceleration of gravity. That's how we define projectile motion. Is motion with only acceleration, constant acceleration of 10 meters per second square in the vertical direction, right? In other words, okay? In other words, this motion it is projectile motion. In other words, it is 2D motion with acceleration equal to 10 meters per second square, right? Along the vertical direction. That's how projectile motion is defined in this chapter. Okay, if you add, if we indicate, for instance, what is not projectile motion for the sake of this chapter, right? For the sake of this chapter, a rocket / missile being propelled during flight, okay, is not considered projectile motion. Okay? However, when the missile runs out of fuel and air drag, right, can be neglected, right? The missile becomes a projectile. Okay? You know, a bullet, you know, a bullet fired by a gun, right, is not a projectile while it is inside the gun barrel. Okay? However, after it leaves the gun barrel, it becomes a projectile again, provided we can neglect air drag. Okay? Provided we can neglect air drag. So those are examples of projectiles. Okay, I'm gonna give you another example, right? Here you go, I have an object here in my hand, right? And this object is moving here in space. It's my clipper. Right now, this object here is not a projectile because you have, it's not subjected just to the acceleration of gravity, it's subject to other types of acceleration as well. But the moment, you know, suppose I propel this object, I'm gonna propel this object into space, right? The moment I release my hand from the object, this object becomes a projectile. While I'm stuck, still in contact with this object during the time that I'm propelling it, it's not a projectile. But the moment it leaves my hand, it becomes a projectile. Those are examples of projectile. Okay? So here you go. Okay, that's what you have to. So we're going to do projectile motion now. Projectile motion, and in the case of projectile motion, in the case of a projectile, it has acceleration only y-axis. It has an acceleration equal to g. I'm not gonna say 10 meters per second squared. I'm gonna say g, okay? Only along the y-axis. So we can start solving this problem with this information, okay? So let's treat it as though it is an example, okay? Example, here you go, example. An object is propelled with an initial speed, I'll call it V naught, the initial velocity V naught, velocity, not speed, let's call it initial velocity V naught, the initial velocity vector V naught, and this is making an angle theta with the horizontal. Okay. What we are going to do here? The object is at the origin of the coordinate system. What does it mean? X naught equal to 0. Find its equations of motion. Equations of motion. Okay. So we're going to treat this projectile as though it is an example. Okay. Find its equation of motion solution. how do we do that? Okay, we start with what we know, right? I already told you by definition that projectile motion is accelerated motion along the y-axis. There is no acceleration along the x-axis. That's why I put 0 here. But that is acceleration along the y-axis, and the acceleration vector is downwards, minus 9.882, right? 82 meters per second squared. Let's see if I can get you an illustration. Oh, here you go, right in here. This is the illustration. Don't forget I'm setting up the y-axis upwards, right? The x-axis is to the right. So here you go. Don't forget, this guy becomes a projectile after there is no force accelerating it. You know? So that's what it is. So that's the acceleration. Okay, and we can also state that the initial velocity vector, okay, is going to be v naught x. V naught x? No, wait a minute. V naught, no, not v naught x, it's v naught cosine of theta x. Make sense? Plus v naught sine of theta y. Right? So here are the things that we know. Oh, there's one more that we know, right? Which is the initial position. The initial position R naught is going to be 0 because the object is at the origin, according to this illustration. You do not want to complicate the situation by putting this object another place, okay? And it's not even necessary to do that because this axis here is like a portable axis. You can put it anywhere that you think is convenient. Okay? So those, and now, yeah. And now we can start the problem, right? So just like we did before, we started with the acceleration. Okay. Notice that we have 0 acceleration along the x-axis. Consequently, along the x-axis, the velocity must be uniform, must be constant. Okay. Since, here, I'm going to write it down here. Since we have, oh, by the way, the motion along the x and y axis are independent of each other. Okay, that's very important. That's an assumption that we make too. A very important assumption. There are more complicated problems that the motion along the x and y axis are not independent. But we don't want to treat those problems. We don't want to treat those problems. Okay, we want to treat the simplest of all problems that has some practical application. The motion along the x and y axis are independent of each other. For this reason, we can say, for this reason, and are independent of each other, and there is no drag. For this reason, we can state the following. 1, the motion along the x-axis will be with constant acceleration, and 2, the motion along the y-axis will be will be with no acceleration, right? With no acceleration, right? Will be with constant acceleration. Uniformly, the motion along the y-axis will be uniform acceleration. The motion along the x-axis will be uniform motion. Okay, uniform motion, and uniform motion means ax is equal to 0, and the motion along y will be with uniform acceleration. Ay equal to minus g. So let's go here. Okay. For this reason, we have forget this guy here, right? I'm gonna here write it like that. We go. Here's gonna be Vx. Here's gonna be Vy. Right? Don't forget it has an x component, it has a y component. We have Vx is going to be constant equal to V naught cosine of theta. And Vy is going to be what? Is going to be V naught sine of theta minus GT. Make sense? Okay, so here you go. Let's look at this drawing here, right? In this drawing, the initial velocity can be broken down like it is has an x component and a y component of the velocity. So it is as though it's being propelled upward. Not only is being propelled in the horizontal direction, but it's also being propelled upwards. Okay? Along those two directions. So we're starting to get the equations of motion for the projectile. Okay. And then, and again, you know, what do I mean about getting the equations of motion, right? You know, I guess it's already, we need, I'm gonna spell it out completely, specifically here. We need to find the following, right? A, we already have the A because we know this is a projectile motion. We need to find V. We have V naught, but we do not have V, right? At the beginning of problem, right? And we need to find R. We have R naught, but we do not have R, which is the genetic position. This one we have it. Wait, this one we just found. And this one I'm gonna find out now. Right? So here you go. And what about the we have a similar situation for the position vector of the particle, right? In the case of the x component of the particle, it's not going to be constant. It's going to be Vx times t, which, by the way, ends up being V naught cosine theta times t. I'm going to even put like that. All right, like that. If I want, you can put the x naught here, but the x naught is 0, right? The x naught is 0. Just like in uniform motion we got before. So at this point in time, you must already have the, the solutions for uniform motion and accelerated motion in your head. But what about for the vertical direction? For the vertical direction, we are going to have, the V naught y times t, right? plus half a, don't forget a sub y t squared. Okay. The v naught yt is v naught sine of theta. Okay, and here what we get? We get minus half g t squared. The minus comes from the g, right? So those are the equations of motion that we have. That's all. And now we're going to work out the consequences of the thing, of those equations. Okay, so if I'm gonna spell them out. Let's see, we have x and y here, right? So let me spell them out. I want to put that in order. Here you go. A, summarizing, right? Summarizing. A is equal to that. Even better, if I want to put it in a more generic sense, right? I put minus g. Summarizing. We start with that. The next one in line is this one here, the Vx and Vy, right? I don't need this constant. I'm gonna put them like that. And finally, we have not like that. Those are the equations of motion. Those are the equations of motion. I can even spell them up in a different way. Okay, I can even spell that up, those equations in a rather different way. And I did it here in my notes, my previous notes, right? So I'm going to repeat them in a different way. Okay, I'm going to repeat them in a different way. And you're going to see that's not difficult to memorize that, provided you have memorized, provided you master, right, the uniform motion and the uniformly accelerated motion. See, v naught plus at, but it's v naught vector. At, a is vector times t, right? And here you go. I'm just repeat what I did before. Here you go, like that. Right? Here, v naught x is going to be not cosine of theta, v naught y, v naught sine of theta. And the other one, here you go. We're going to write down in terms of the vector r. Okay? Just like before, right? I'll spell out like that. X equal, oops, constant velocity. Oops. Why I didn't do that? Let's see. Okay, now I did it. Okay. And broke it down, constant acceleration. Constant acceleration. Isn't that nice, this notation here? Right? Vectorial notation. Compare that with the what we saw for one-dimensional case, right? For one-dimensional case, for 1D case, we had, we had exactly the same thing. Was just it happened that was not a vector, right? A minus G, right? V without the vector. Without the without the vector A without the vector, right? And for the one-dimensional case of the acceleration, right? Accelerated, constant acceleration was like that. X, right? V naught t without the sign of theta because it's a 1D motion. And I want to put the more generic equation here. Let's not forget that R naught is 0, right? Don't forget that R naught is 0. So let me erase that. This equation here is not much different from this equation here, right? The only difference is that it's a vector. This equation here is not much different from this equation here, right? The only difference again is that it's a vector. Okay. So now we have the equations of motion. Okay.
Professor, I have a question.
Yeah.
So the vector of displacement, right? Vector R, right?
Yeah.
That's when you try to get the value, you didn't include the what's that called? The R vector R not 0 because it goes 0 all the time.
Well, it depends. All depends on the problem. Okay. For this
Okay.
problem of projectile, we can set the initial position. Is not the vector R, right? It's the vector R naught, right? The initial position as being 0. Okay. It goes from problem to problem. For this specific problem, we can set the initial position as being 0, but not the initial velocity as being 0. The initial velocity cannot be 0. Otherwise, the projectile doesn't move anywhere, right? It goes from problem to problem. Okay?
Okay. But I have a question.
Uh-huh.
I have another question. So when it comes to real solving problem, right?
Uh-huh.
How come when you apply gravity, most of the time you just get rid of the minus and use like 9.8 meter per second square?
You're asking how come some problem has this negative sign here, right?
Yeah, I mean, how come we don't even use that? But it needs to be negative, right? Because it's going down, which is negative direction, right?
Yeah, it is negative. In this specific problem, it is negative because the y-axis is upwards. Okay.
Right. Oh, okay.
If you set the y-axis upwards, the acceleration of gravity is going to be negative. But if you choose to set the y-axis downwards, then you do not have this negative here anymore. Okay, it's going to be something like that. Let me, if you choose, to your y-axis to be downwards, right?
Mm-hmm.
Right in here. Now here is going to be from downwards is going to be positive and upwards is going to be negative, right? See that the direction of the y-axis is in the same direction of the acceleration vector, right? So
Mm-hmm.
now you have to set up your acceleration of gravity vector as being positive. It all goes according to how you choose your axis. You still get the same result if you do that. Okay?
Oh, okay.
And you still get the same result.
So we always have to look for the direction of the arrow, like when
you have to look for the direction of the axis, right?
Okay.
The acceleration will always be downward. Now, how are you going to choose? Are you going to choose the x downward or the x upwards? In general, we choose the x upwards, right? In general. Only in very rare instances we end up choosing the x downwards. Very
I, and I have one more question. So
Mhm.
different between one-dimensional delta velocity and two-dimensional velocity is like the first dimension is like x, let's say x final minus x initial, but the second dimensional is like x plus y, right?
Yeah, it's gonna be two separately, right? It's gonna be one equation for x and another equation for y, right? That's the
Oh, okay.
difference. That's so here you go. In this two-dimensional problem, we end up having almost twice as many equations, right?
Mhm.
We have two, four, 5 scalar equations. We do not have 6 scalar equations because the x component of the acceleration is equal to 0, right?
Oh, okay.
Okay, so if we are dealing with a two-dimensional motion, we're going to have twice as many equations. If you're dealing with three-dimensional motions, we may have 3 times as many equations. Okay, the more dimensions you have to the problem, the more equations you have. Okay,
Oh, okay.
so let's write that down here, right? Note that a 2D problem may have as much as 6, right? 6 equations of motion. 2 for the acceleration, right? 2 for the velocity and 2 for the position. At most, right? May have at most 6 equations of motion, 2 for the acceleration, 2 for the velocity, and 2 for the position. Likewise, right? Likewise, for a 3D problem, let's see, we're going to have 3, 6, 9, right? We may have at most 9 equations of motion, right? 3 for the acceleration, 3 for the velocity, and 3 for the position, right? The acceleration here would be ax, ay, ad. Okay, vx, vy, vz, and 3 for the position, x, y, and z. Okay.
Well, what about four-dimensional?
And
How
then,
many equations can be put
well,
there?
then it would be 12, right? Then it would be 12. Okay. So then it will be 12, just like in special relativity, right?
So it goes by 3 times, like,
Yeah.
oh, okay.
3 equations of motion, 4 for each, right? In special relativity, we have x, y, z, and t, right? Special relativity. But we're not going to get into that. That's for next physics, then physics 7.
Oh, okay.
Okay. Oh, let's see. So now we are going to apply. We are going to do another example. Okay, so notice that the first step was to find the equations of motion for a projectile, right? That's the first step. Once you have the equations of motion for the projectile, you can find other things. You can find other things, yeah. Okay. And this equation that you see here, okay, I'm going to write it down in a different way. Is what we call the parametric equation, okay? It's a set of parametric equations. The A is constant. Oh, no, not this one. I don't want this one. I want the other one. I want this one here. Okay. Okay, here you go. Here's constant, right? This vector is constant. And I'm gonna put a vector symbol on this guy. Oh, yeah, man, he didn't put it in. Okay, okay, that's good. Constant. We have, now I'm gonna write that down in terms of, let's say it's also, this guy is also a function of t, right? It's not exactly a function of t because it's constant. This one is gonna be, let's see, a function of t as well, right? Okay. This one is going to be a function of t. And this one is going to be another function of t. Okay?
What is
Yeah.
h?
Huh?
Is it height? H?
H is let's see, where H? Here?
Yeah.
No, I'm saying that is a function of t, right? Function of t, is denoted by this symbol, right?
Mm-hmm.
Actually,
Okay.
strictly speaking, right, this one is not a function of t. This is a constant. This is another constant. Let's call it constant prime. Constant prime. Okay, Fg. And let's call this one h. Let's call this one h. But this one is a function of t. What you have here, is a set of parametric equations. Okay, because each one of those equations is a function of the same variable, because each of these equations is a function of the same variable. Okay, we study that in math, parametric equations. Okay, but in the next example, we're going to write y as a function, put f prime, right, of x. It's possible to do that. Okay, and that's why we're going to do that, and that's what we're going to do. When we write y as a function of x, when we write y as a function of x and plot it, we get the path of the projectile in the y-x plane. Okay, and that's what we're going to do now. And that's what we're going to do now. So that's going to be our next example, right? Example. Here, right? No, not here, right. Write y as a function of x. Okay. Using the equation of motion above, write y as a function of x. That is going to be my next example. I'm treating that as though as an example. Okay. So what we have to do, let's see, I have to copy those two. Okay. Remember, I just want to write y as a function of x. So all I need is going to be those, no more than those two equations. Okay. And like that. is our starting point. Okay? In order to write y as a function of x, comma, we must eliminate t from the system of equations above. From the above system of equations, from the above system of equations. Or okay. No, see, we have x as a function of t. We have y as a function of t. But now I want y as a function of x. So what we have to do? We have to somehow eliminate t from the equation. From the equation. And it's not difficult. For this type of problem, it's not difficult to do that. It's not difficult.
Professor,
Yeah.
I have a quick question.
Yeah.
So you wrote y equals f prime, right?
Yeah.
Can-
Yeah.
Yeah, there.
Because this f prime is different from this f, right?
Yeah, but
That's why.
in order to find the value, can you use like derivative to find the value? Like
No, we're not going to use derivatives. No, we're not going to use derivatives. The
okay.
prime here doesn't mean derivative. The prime here means a different function. Okay,
Okay.
that's what the prime here means. I'm going to even put like a ff. Okay, so you know that this one here is different from this one. Okay, so we have to somehow eliminate t. So you have two choices here to eliminate t. Use the equation of motion y as a function of f x. Let's see. X given v naught, g, and theta, right? You have to know that too. Given v naught, g, and theta, right? Write y as a function of x. That's given v naught, g, and theta, write y as a function of x using the equations of motion. The equation of motion. Okay? So you have two choices here. Okay, since you have two equations, you have two ways of eliminating t. You either write t as a function of y. In this case, it's going to be a second order equation, and it's going to be difficult to handle. Or you write t as a function of x and substitute that here. Okay. It's far easier to eliminate t from this equation here. And then you substitute here. But if you want, you could have done for that one as well. But it's going to be far more work because you have to deal with a second order, the solution of a second order equation.
Professor, I have a question.
Yeah.
So when it comes to x-axis, you have to use cosine theta, right? And
Yeah.
y is equals sine theta. Oh, okay.
That's right. But don't forget that all depends on how you define theta, right? In this specific problem, I define theta as being the angle between the x-axis and the vector velocity. Okay, that's why it ended up as being cosine of theta. It ended up being cosine of theta because I defined the theta as being this angle here. Okay, so you must always keep in mind, or you must always have to come up with a drawing. Okay, to get the right sine and cosine relation. Okay, if you had defined the theta angle as being this angle here with the vertical, then it would be all the way around. Okay? And sometimes it's convenient to do that, but we're not doing. Let's see, weight. I'm going to put a little bit more of weight here. Yeah, here you go, thicker. Okay, so let's go for our next step. I'm going to eliminate t. Eliminate t means what? Write t in terms of x and the other parameters that we already know. Here we go. Theta. Makes sense? Right? T is x divided by v naught cosine of theta. And by the way, I'm going to, better. X divided by v naught cosine of theta. And then what you're going to do? we're going to plug this relation right in here, right? Right in here.
Wait, I have a question.
Yeah.
So you wrote t equals x over velocity initial velocity cosine theta, right? Isn't
Yeah.
it x is as same as the initial velocity times. Oh, okay. It's kind of a bit different, right? There's I have
Yeah.
to multiply velocity and times, right?
Yeah, I'm changing the format of this equation. That's all I'm doing. Right?
Oh, okay, okay.
I'm just changing the format of this equation because I want to eliminate t from the two equations. I want to eliminate the parameter
Oh, okay.
y as a function of x, right? And
Oh, okay.
that's exactly what we're going to do now. I'm going to put this guy here. I'm going to replace that as a parenthesis. This one too, I'm going to replace as a parenthesis. There's a reason why I'm doing that, right? Why is that? Because I'm going to plug this t right in here. Make sense?
Yes.
It's just a recipe, right? You follow everything in a logical manner. Sometimes it's difficult because it's too much work. That's why it can be difficult, right? It's not that math is difficult. It's because some problems requires too much work, and you get burned out deriving equations and so on, right? So this one, huh? You can see I'm going to square this one as well. I'm going to square this here. I'm going to square this here, right? I'm distributing the squares inside the parentheses. And now, think about that. We used to do all of that by hand in my time, right? And we always would incur in errors, in mistakes. That was very difficult to track down the mistakes. But now we have those computer programs. Now we have even algebraic manipulator software that I love to use, okay, to decrease, to speed up your derivation process and make it look nicer too. Not just speed up the derivation process, but make less mistakes as well. Okay, the V naught here. Okay, let's see here. This V naught here cancels out with this V naught here, right? Not only that, but this cosine of theta can become combined with this sine of theta, right? Here I don't see any simplifications that we can do. There's no simplification, but here we can, in the second equation here, we can simplify, right? I'm going to eliminate this V naught. And then I'm going to transform my sine of theta into tangent of theta. Okay, like that. And now we got our equation, our solution of y as a function of x, right? Then let me put everything with the same color now. Good. This is what I call my y as a function of x. Let's see, ff, huh? X. This is what I call my y as a function. We have a y, an x here. We have another x here. And I'm going to simplify that even further. This term that you see here is a constant because it's the initial, is the tangent of the initial angle. What changes here is the x. And this thing here is also constant, the initial velocity, right? And the initial angle squared. There you go. Okay. Okay. This is a constant. This is a constant. Okay. It looks kind of messy, right? But it's not that messy at all. If you look very carefully, you will be able to recognize that this equation that you see here is the equation of a parabola. Okay, here you go. I'm going to put tangent of theta. I will call it A. And this whole mass that you see right in here, I'm going to call it B. A and B are constants. Okay. And so what we get here? We have here a parabola, an upside down parabola, because of this negative sign, right? Because of this negative sign, the solution that you are getting is an upside down parabola. Do you see that? Okay. If we have the values for V0, theta, G, and G, we know how to plot this graph. You know, and let's see if I have it here now. Let's see, we're supposed. Yeah, that's so odd. I don't have it. Okay, I'll have to do this from scratch. I have 6 minutes to do that. Ah, gosh, why is that? Strange. Let's go up, 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 up. Yeah. I do not know why I don't have it. I'm supposed to have it. Nope, overshoot it. This one, no. No. This one, okay? So let's see if I have in the other one, so I don't have to repeat it. The drawing. You know, I'm gonna show us in the book. It's better, so I don't spend too much time doing that. So let's see. Do you see those water fountains? Huh? Those water fountains is drawing an approximate parabola. Each of those droplets of water that you have here in the nozzle exiting the nozzle of the water fountain is a projectile, and the path it is depicting is that of a parabola, approximately a parabolic shape. Okay, and let's see if I have it here. He didn't start with projectile motion. He didn't start with projectile motion. He started with something else. Okay, here you go. Here's the case of the plane dropping a package, and this package behaves just like a projectile. Okay, let's see. Let's see if they have a more generic. Okay. Oh yeah, here you go. That's the one. That's what we did. Okay. An object being propelled at the initial velocity that makes an angle theta with horizontal. That's going to be the path of the projectile. Okay, and I'm going to draw here for you. See here. Okay, it's going to be somewhat like that. It's not exactly a parabola, but why it doesn't go up? Okay, yeah, okay, goes up and go up and down, right? Yeah, here you go. Yup, right here. And this velocity vector must be tangent to the path, right? Initial velocity vector must be tangent to the path. It's not exactly a parabola, but it's enough for you to believe, to understand what is going to be the parabolic path. Okay. Note, see that in this case, see the acceleration vector points towards the center of the concavity, right? No matter where you are along the path, at this point in time, the acceleration vector points towards the center of the concavity. At this point here in time, again, it points toward the center of the concavity and so on, right? Not only at this point here at maximum height, the acceleration vector has no tangential components whatsoever, right? Do you see that? There's no tangential component for the acceleration vector. At this point here in the trajectory, the acceleration vector has a tangential component that is against the velocity vector, right? Do you see that? We have a velocity vector here that's going to be, I'll call that not V0, but I'll call that V1. Okay? Because this acceleration vector has a tangential component that goes against the velocity vector, it means that this velocity vector is decreasing in magnitude. Okay? But on the other side of the trajectory of the parabola, let's say at this specific point here, what do you have? We have a velocity vector that has a downwards component, right? Would be better that we've even changed the color, right? So you go. I'm gonna put the velocity as a red color. Red color. One more minute to go. Red color, red color, red color. Yep. Now, because this acceleration vector has a tangential component, what does it mean? It means that this velocity vector is going to increase in magnitude. Make sense? Okay. Okay, it's 12 noon right now, and there's more things that we can do with this problem. Okay, and then we'll continue with that next time. Any questions? Okay. So don't forget, let's see, someone asked me a question. Okay. No. Oh, no, nobody asked me a question. Okay, so you can stop now. And I see you on Wednesday for our exam. Okay, don't forget the exam starts at 8:50. I'll post it in Canvas.
Hello?
Yeah.
Professor, I have a question about the lab hard copy. When is the due? Is it due?
Both of them, both the spreadsheet and the hard copy are due next week, Wednesday next week. Yeah.
Hard copy. Oh, okay.
Yeah, it's here in the syllabus, right? I see report lab 1 due. See that?
Okay.
Report lab 1 due. And then we do lab 2, accelerated motion. Okay. I have a question, Camden. Okay, did you ask your question already, Camden?
I have more questions to ask you, so I'm going to stay here for maybe 10 more minutes or something.
Okay. Okay, so again, if you want to stay around for asking any questions, let me know. I'll be here for 1 hour.
Okay, so am I allowed to ask you a question right now?
Sure.
Okay, so it's from a homework.
Yeah.
And I was wondering, like, when do I need to use square velocities? I mean, not square, delta velocity square formula. Like, why? What's the purpose of this formula? Is it like to find the initial velocity, or just the?
You're asking about this equation here, right?
Yeah. It's like you know, the homework chapter 2 question 9.
Wait a minute, let me write that down here. Wait, they're talking about this equation here, right?
Yes.
Okay, so yeah, what about this problem? Which problem are you referring to?
So question chapter to homework to question 9.
Question 9. Do you want to share
Point.
the screen with me?
Oh, okay, sure. Let me. I wrote it down, but
Yeah.
I'm going to. And I
Well,
also have.
I
Yeah.
can go here too in the homework. Let's see. Let me stop recording first. Stop sharing. Let me stop recording.